We will now consider rotational motions in 3 dimensions, which is known as the particle on a sphere description of rotational motion. So again, we consider a particle of mass m, and it moves anywhere on the surface of a sphere with a constant radius r, and the potential energy on the surface of the sphere is equal to 0. So you can imagine a soccer ball and a bug walking on the soccer ball. So this is the type of motion that we are talking about. And we can use this model for rotating molecules, for example HI. This is an example that we will consider, as well as the motion of electrons in an atom, which can be considered to be equivalent to a circular motion, or electrons in small clusters of atoms. Now in this case, the wave function should match a path over the equator and also over the poles. So the wave function should be 1-to-1 anywhere on the surface of the sphere. So in this case we need a second quantum number. Phi was the angle that we used to describe the particle on a ring, so in the xy plane, the 2D system, and we're now going to introduce the angle theta to describe the angle over the poles. And we're going to see that a wave function is a function of both theta and phi, as indicated there. So we will need a second quantum number. Now, because we're dealing with 3-dimensional rotation, the Hamiltonian has to consider 3-dimensional system, and in this case we actually have to introduce this symbol, which is the partial derivative to x, y and z. It's also known as del squared, or the Laplacian. You don't have to worry about this. We're not going to use this in calculations, but just remember that we're dealing with 3 dimensions now, which is the second derivative to x, the second derivative to y, the second derivative to z. These are partial derivative signs, so instead of using a d, we use this partial derivative sign. Okay, so our wave function, like we said before, is a function of theta and phi, and we have to have 2 quantum numbers. We've seen ml before, and now we introduce a second quantum number, l. And now we can give these quantum numbers names. L is known as the orbital angular momentum quantum number, and it can take any value from 0 to infinity. ML, we will also now give a name. It's known as the magnetic quantum number, and in this case the values for ML are a bit different compared to the particle in a ring. ML is determined by L. So the values for ML runs from L to minus L, with decreasing by a value of 1 each time. So it's different from what we had for the 2D system. So what do the wave functions look like for a particle on a sphere, or a 3-dimensional rotational system? Well, these wave functions are known as spherical harmonics, and the reason why they have this special name is because these are special functions in mathematics, and these wave functions you will get from a table, so you don't need to be able to derive them even. You just get them from the table. Depending on the value of L and the value of ML, you can just read off the specific wave function. Now in mathematics, spherical harmonics are typically indicated by a symbol y, a function of L and ML, and the angles that we use are theta and phi. So we're actually not going to use the psi sign for the wave functions, we're going to stick to the spherical harmonic sign symbol, which is y. So this is an exception. For 3D rotation, we're going to use that expression for the wave function. So this is equivalent to the wave function. So these are the wave functions for three-dimensional rotation, and they have been normalized. Now for each value of L, there are 2L plus 1 values of ML. So let's just look at an example. Let's say L is equal to 2. ML, we said, is determined by L. Minus 2, minus 1, 0, 1, 2. Because ML runs from minus L to plus L. Minus 2 to plus 2. And we said there are 2L plus 1 values. 2, L is 2, plus 1 is 5. 1, 2, 3, 4, 5. Okay, so that rule works. So for each value of L, there are 2L plus 1 permitted values of ML. This figure just shows the signs of the wave function, where the shading indicates a positive wave function and the lighter color a negative wave function, and it shows you how the wave functions change sign on the sphere. And this is the z-axis. So the z-axis is in that direction each time. So we have the wave functions. What about the energies? Well, the energies are given by this equation. Again, we're not going to prove these energies, you're just going to accept this. So this is the energy equation for a particle on a sphere. And you'll notice that these energies only contain one quantum number. Remember, we have two quantum numbers, ML and L, but ML does not appear in this equation. We definitely have quantization because the quantum number L is present. It's independent of ML, and we've already said that there are 2L plus 1 different values for ML for a specific value of L. And all of these will have the same energy because energy is only determined by L. So if we go back to this example that we looked at, energy is determined by L. So each of these will have the same energy because ML does not determine energy. And that means a level with quantum number L is 2L plus 1 fold degenerate. So this level has quantum number 2. 2L plus 1 is 5. So it's 5-fold degenerate because there are 5 different ML values and they all have the same energy. So that's how the degeneracy is defined. We can now use this energy expression and combine this quantum mechanical expression. Remember, it has a quantum number, so it's definitely quantum mechanical, with the classical energy expression given here. So this is classical, to obtain an expression for the magnitude of the angular momentum. So classically, we can use that expression. Quantum mechanically, we can use that expression. And these two must be equal. So in that case, J squared is equal to L plus 1 H bar squared. And if you take the square root on both sides, one can get the magnitude of the angular momentum, and in this case L is 0, 1, 2, etc. So here we have an expression for the magnitude of the angular momentum. We also have an expression for the z component of the angular momentum Jz from the two-dimensional case, which is equal to ml h bar. So this is the z component of the angular momentum. And what we'll see in these wave functions is that the number of nodes increase with quantum number L, because the higher the angular momentum, the higher the kinetic energy, which results in a more buckled wave function and more nodes. So if we express that as an increase in quantum number, increase in angular momentum, increase in energy, because if you look at the relationship between energy and angular momentum, it only has kinetic energy, there's no potential energy, and that would imply an increase in the number of nodes. So that is why we have this relationship. So let's have a look at the application of this model to a chemical system. So in this case we consider the rotation of an HI molecule. And because of the large difference in atomic masses, it's appropriate to picture the hydrogen atom as orbiting a stationary iodine atom. So we consider the iodine atom as stationary, and the hydrogen atom basically orbits around this iodine atom, the hydrogen atom, and we consider this to be a three-dimensional system, three-dimensional rotation. The distance, this radius, is equal to 160 picometers, 10 to the minus 12 meters, which is the equilibrium bond length. The first part of the question asks us to calculate the moment of inertia of the system. So we have all the information that we need. A part of the question, that is moment of inertia. And we're only going to use the mass of the hydrogen atom because that is the only part that's moving. We consider the iodine atom to be stationary. So now we need the mass of a hydrogen atom, and it's not given. So how do you calculate the mass of an atom? Well, basically, you use the mass from the periodic table times the MO unit that is given in the data sheet, which is 1.6605 times 10 to the minus 27 kilogram. So with that information you can calculate the mass of any atom. And once we have that, radius squared and there we have the moment of inertia for the system. Second part of the question asks us to calculate the energy of the first four energy levels. So we have just seen the energy expression independent of the quantum number ml. Because we have this part in this expression that we're going to use for all four energy levels, let's just calculate that first. Okay, and now we can apply that to L equal to 0, 1, 2, 3. The 1, 2, 3, 4th energy levels. So energy 0, L is 0 times 0 plus 1 times h bar squared over 2I is just 0. E1, 1 plus 1 times 1.297 times 10 to the minus 22 joule is equal to 2.594 times 10 to the minus 22 joule. E2 you can calculate, that is equal to and E3 minus 21 joule. So there we have the energies of the first 4 levels. The C part of the question asks for the degeneracies of the energy levels. So those are the first 4 energy levels. So for L equal to 0, 1, 2 and 3, we know that degeneracy is given by 2L plus 1. So for L equal to 0, the degeneracy should be 2 times 0 plus 1 is 1. For L equal to 1 it's 3, for L equal to 2 it's 5, and for L equal to 3 it would be 7. The D part of the question, the magnitude of the angular momentum for the L equal to 0, 1, 2 and 3 levels. So we've derived this equation. That is the equation for the magnitude of the angular momentum. So for L equal to 0, 0 times something, it's just 0, h bar. For L equal to 1, it's 1 plus 1 to the power half h bar. So that is square root of 2 h bar. For L equal to 2, square root of 6 h bar. For L equal to 3, square root of 12 h bar. You can check that. Next part of the question, the separation between L equal to 0 and L equal to 1 levels. Now in the first part of the question, we have already calculated these energy levels. So for the E part, we want delta E between E1 and E0, but we have these energy levels. E1 we found to be 2.594 times 10 to the minus 22 joule, and E0 was just 0 joule. So in this case, the F part of the question then asks you what is the frequency of a photon required for a transition between these two levels. So that's the frequency. So the frequency is delta E divided by H, 2.594 times 10 to the minus 22 joules divided by 6.626 times 10 to the minus 34 joules per second gives you a value of, and there is the frequency of the photon for a transition between the rotational level E0 and E1.